In this video, we're going to get a little further into Rayleigh's criterion and try to start to understand a formula that he created to predict the separation between objects and whether we can resolve them or not. So just go over a few things. Here's a picture of a grid of lines that I could draw on a piece of paper. And those lines are placed pretty close together. And if I step back about 4 or 5 meters from the screen, you can even try this, those lines would become pretty blurry. But if we take a magnifying glass or we put our eye right up to the screen, we start to see that those lines become clearly visible. They're resolved compared to these lines over here. So rules of thumb is that resolution is limited by diffraction. We learned that in the last video. So diffraction causes the spreading and the overlap of the images in our eyes. But we can improve resolution when the two objects are separated by large distances between each other. And we can also improve resolution when we bring those objects closer to our eyes. So Rayleigh's criterion tries to figure out how these two things on the bottom here really cause that. And what he describes is angular separation. So when I take a look at these two objects, the yellow star and the red star, I don't really define how far away they are from each other. I'm looking at the angle that those two objects subtend on my eye, form between here. Okay, so that angle is my angle of separation, the separation of the two objects, the light that is reflected on them, that they subtend onto the pupil of my eye would be that angle. And that angle is the same angle that the central maxima would form, okay, between the central maximum from that and the central maximum of that. That angle would be the same as that angle based on geometry rules. So that's the angle that is being subtended. So Rayleigh tried to make a relationship between that angle of separation, that angular separation, and understand what is the minimum angular separation that I can have in order for these to be resolved. So you can imagine as that angle becomes smaller, okay, so if I would draw lines that are smaller, okay, imagine that these two stars got closer together. That angle that is formed, that angle that they subtend, I'm going to call it theta prime, is a lot smaller. Okay, and because it's a lot smaller, what we end up having is those diffraction patterns overlapping in the back of the eye, creating an orange image. So what Rayleigh was trying to figure out was what would be the minimum angle that I can get such that these two diffraction patterns are involved. That's that theta min. So what limits it? Okay, obviously what limits it is diffraction. And what Rayleigh said is that the central maximum of one object has to overlap the first order minimum of the other. Okay, so basically the formula for diffraction will apply. Okay, so somehow this formula of diffraction will limit that angle, the angular separation between these two objects. Okay, and we're going to talk about that in a second. Okay, so in Rayleigh's criterion, he came up with this formula. The minimum angle that those two objects can subtend on my eye is equal to the ratio of the wavelength of light that is reflecting off those objects divided by B. Now B is my slit width, okay? You'll notice that, well, where did B come from? We usually have D in the diffraction formula, and D is my slit width. Well, they use B in this formula because you'll see to calculate the angle, there's another D in there, and they didn't want to confuse it. So B in this formula is my slit width from the aperture that's causing diffraction. All right, that's an important thing to write down in your data booklet because lots of kids get confused with the changing of symbols in the IB data booklet. So B is the slit width. B would be the diameter of the pupil at that point. Okay, and lambda is my wavelength. So how does that work? How does lambda over D or lambda over B give me my minimum angle? I can see in this formula over here, I got lambda, I got D or B, as I would call it. So that's in that formula. So if I rearrange this formula, lambda over D is equal to sine theta. Oh, I can kind of see a resemblance. I got a theta on that side. I got lambda over D on that side, but I have an N and a sine. Where did they go? They're not here. Where's the sine and where's the N? So let's just talk about that for a second. So let's imagine, let's just make things simple and let's just take a look at the light coming off of the yellow star towards the eye. And what I'm going to do with the eye is I'm just going to make it flat. Okay, so here's, imagine that's just the pupil part of the eye. And the light coming from that star is going to diffract and form a central maximum on the back of the eye, and then the first order minimum, okay? And what we have to remember is, I'm just gonna use a different, we have to remember this triangle. So for single slit diffraction, we have this triangle that we formed if you go back a few videos to understand single slit diffraction. And the angle for d sine theta equals n lambda, okay, that angle that we're talking about over here is the angle between the center of the central maximum and the first order minimum, because it's destructive interference. Okay, so it's destructive interference that we're talking about. So the angle here is going to be that, all right? And that angle is what Rayleigh was talking about. The angle that the other star has to be, so let's make it red, okay? The angle that that other star has to be at that place so that its central maximum can be there, right in the first order minimum. So that angle here, this angle that we just calculated using this formula, is that angle based on geometry rules. They're the same angle. So this d sine theta formula based on the slit width, okay, the slit width over here, n is going to be 1 because that's my first order minimum, and the wavelength of light coming off. I'd be able to calculate the angular separation here based on diffraction, and that angular separation based on this formula is equal to the angular separation of those two objects. Okay, so what does that angular separation mean? Those two objects are going to form a wedge. Okay, so let's just say I had these two stars. They're going to form a wedge with an angle separating it. And if that angle was very small, this side here would correspond to the distance, okay, this distance that those objects are away from my eye, and the arc length over here corresponds to my separation. Okay, so if we remember from math, S, the arc length, divided by d is equal to theta in radians. Okay, if you remember. So what this formula, this is really important to understand, is that if I have my separation between those two stars, linear separation, S, and I divide it by the distance that those stars are away from my eye, that will give me my angular separation. And that angular separation is measured in radians. Very, very important. So angular separation is measured in radians on my calculator. And that angular separation in radians corresponds to the single slit diffraction, where n is equal to 1, which gives me lambda over b. So you don't have to really know all this stuff. This is really nice if they ever ask you to derive or explain it on an exam. You know, how does it relate to diffraction? All you really need to know for resolution is how to apply this formula that's inside of your data booklet. So theta minimum, which is my angular separation in radians, is equal to the ratio of the wavelength of light divided by my slit width. And that's it, okay? So then if I took my slit width and I multiplied it by the angular separation, that would give me my wavelength, okay, of light, the minimum wavelength of light, and so on. You can play around with that formula, okay? And another thing to think about is my linear separation divided by the distance. So this is the distance that is separating, the linear separation divided by the distance that is separating those two objects from my eye is equal to my minimum angular separation, which is equal to lambda over b. So I'd be able to calculate whether two objects can be resolved if I measured the distance between them, and I knew the distance between the objects and my eye. I'd be able to actually calculate, based on the diffraction formula, whether they would satisfy Rayleigh's criterion. So in the next video, we're going to do a bunch of practice problems using and applying this formula. Okay, so I'm sure that this is a little confusing as we go through all this stuff, but once we start putting numbers into it, it should become a lot easier. But you can pause this, go back, and I would watch this derivation again 2 or 3 times just to have an understanding of what these variables mean. a question you can ask yourself is, what's going to happen to that minimum angle of separation if I use a smaller wavelength? Instead of red light, what if I looked at an object with blue light? How does that affect my resolution? What effect does opening my pupil diameter have on my resolution, increasing the slit width? What does that do to the minimum angle of separation that these things can be apart from? Okay, and how does that affect the linear separation, S, or the distance at which I can see an object and have it resolved? Okay, now, an important thing that we need to talk about is that your eye has a circular opening. And when you shine light through a circular opening, it doesn't form the diffraction pattern that we're used to seeing, which would be these little kind of squarish dots on a screen that look like that. Okay, those squarish dots that would be formed on a screen when we looked at diffraction from multi-slits and everything else like that, those patterns are formed when I shine light through a square or a rectangle. Okay, but if I shine light through a circular opening like our pupil, it forms these concentric rings. Now, based on the fact that circles are very different than boxes and are not linear, it happens that the separation of these lines is a little greater than what I would predict with the regular diffraction formula. The separation is increased by a factor of 1.22. So if you look in your data booklet, you'll see two formulas for resolution. You're going to see this formula, and this formula applies if my hole is a rectangle or a line, okay? That's for regular diffraction if I'm shining light through a square or a slit. But if I'm shining it through a circle, like the pupil of my eye, it makes a circular diffraction pattern on the back of my eye that has a 1.22 times the spreading of those maxima. So the actual formula for circular diffraction has a factor of 1.22 in front of it. So you need to remember, when you're looking at a resolution problem, they'll tell you whether it's going through a circular hole, then you have to use this formula. If it's going through a rectangle or a linear hole, then you would use this formula. Okay, so I have a larger requirement here, okay? So I'd have to factor that in. All right, in the next video, we're going to do some actual calculations and see how to apply these formulas.